So this lecture is intended to give us a basic idea of how friction works and behaves in the physics classroom and in our problem solving. Um, we're going to hope things go smoothly, but if you have a rough time, well, it's friction. One of the first things we have to recognize about friction is that it comes in several different types. So we can see right here in this simulation that we have a crate, and the crate is experiencing a balance of forces, gravity and the normal force. And there doesn't seem to be any friction force acting on the crate. Now we have this guy come along and begin to exert an applied force on the crate. So notice now he's pushing the crate to the left. And his applied force can vary. I can make it large or I can make it small. And what's interesting is that we get this friction vector that's always exactly the same size as his push. If he doesn't push, there's no friction. And if he pushes hard, the friction gets harder as well. So this is this sort of adjustable friction that keeps an object at rest or keeps the net force zero is called static friction, and it involves the gripping of the surface, the box, to the surface that it rests on. However, if he pushes hard enough, he can eventually make this thing break free. And if you look closely, notice that the friction force momentarily decreased, and now it's staying constant no matter how hard he pushes. And even if he lets go, that friction force persists until it runs into the wall. So we move into a second type of friction that doesn't adjust itself size-wise, and this type of sliding or moving friction we call kinetic friction. There are other kinds of friction as well. Two others you should be familiar with conceptually are rolling friction and drag. Rolling friction occurs when a wheel rolls along a surface and deforms, or if a road deforms underneath of the wheel. Can cause some resistance. And then drag or fluid resistance is sometimes grouped with the other types of friction as a type of friction, even though it can be fundamentally different. But you could argue that it can be grouped in with friction as well as a resistive force. If we try to understand why friction happens and why it always results in objects getting hot, and we got that picture there from Tom Hanks in the movie Castaway creating a friction fire by rubbing sticks together. Let's take a closer look at a couple of textbooks. So in this simulation, it looks like somebody, horror, has placed a chemistry textbook on top of a physics textbook. And we can zoom in on the interface between the two, and we can actually see the atoms in the chemistry book and the physics book, or at least a model of these atoms. And not being at absolute zero, we can see that they're twitching around. When we take the chemistry textbook and we bring it near to the physics textbook, we notice that the atoms never come into contact. After all, they have negative electron clouds outside of them that repel each other. But these electron clouds push on each other, and as I rub them across each other, notice that they get excited or perturbed. The energy carries throughout the matter and the temperature rises. So if we really rub them together, we heat it up so much that the chemistry textbook vaporizes. Come on, chemistry, if you can't stand the heat, stay out of the kitchen. At the end of the day, friction is an important topic, and understanding it mathematically is important to engineers and biologists, biomechanists, people that, rock climbers, or even just everyday life. You think about life without friction, you wouldn't be able to walk or tie your shoes or anything that requires surfaces to grip each other. Um, so it seems like we spend a lot of our life either taking advantage of friction or trying to minimize it. Well, let's take a look at, from a physics standpoint, how we might model it mathematically. So let's consider what happens to an object when it experiences friction. So imagine we were to take this box and try to pull it along the surface at a certain velocity v. If we zoom in on the interface between the two surfaces, we'll see that no matter how smooth the surfaces appear to the eye, when looked at close enough, all surfaces have some texture to them. These little teeth are going to catch on each other and exert normal forces on each other in such a way the sliding object and the ground experience net forces in the opposite directions. The net force in the backward direction on the box we see as a friction force, and of course the ground receives an equal reaction friction force in the forward direction. Now if we take it in another level, we look a lot closer, we find that these surfaces are made up of individual atoms. When these atoms come nearby each other, they perturb each other, excite each other, and this results in heat. these atoms bump into each other. The first type of friction we're going to look at is called kinetic friction. Kinetic friction is a moving or sliding friction, and our symbol for this type will be F sub k. This friction acts to resist relative motion between moving surfaces. So as surfaces slip or slide past each other, this friction creates a resistive force. Though this isn't always true, this force of kinetic friction is typically a constant force over a range of speeds and temperatures where no matter what rate the surfaces are sliding past each other at some relatively constant value. This is called Coulomb's law of friction. Second type of friction is static friction, which involves surfaces at rest relative to each other. We'll use F sub s to designate this friction. This type of friction force is adjustable. It will adjust itself to be whatever size it needs to be to keep the surfaces at rest. But it does have a limit, and this value is very important. We're often interested in figuring out what this maximum force of static friction is. In most cases, for a set of surfaces, the force of static friction is larger than the force of kinetic friction. In other words, two surfaces at rest and gripping each other will exert a larger frictional force than two surfaces that are actively slipping or sliding past each other. There's a resistive force called rolling friction. And if you've ever ridden your bike along soft or gravelly ground, you know you can felt this resistive force as you pushed gravel out of the way, or if your bike tire begins to get flat. The deformation caused by biking with a flat or a low air pressure tire creates some extra resistance. It's one of the reasons why cars get worse gas mileage when the tire pressure isn't high. Fluid friction called drag is very difficult to model and a lot of times has to be tested experimentally. But in many cases, particularly with air resistance or even water and objects that aren't moving very slow, drag tends to vary based on some constant and the speed of the object squared. So in general, the faster an object moves, the larger the drag force becomes. So when we consider a falling skydiver, when they first begin to fall, it is only the force of gravity acting on them. As they begin to pick up speed, the drag force grows. Eventually, they're going fast enough that the drag force is at the same magnitude but opposite direction of gravity. Since those forces then cancel each other out, the skydiver stops accelerating. The rate that they're traveling when this happens is called the terminal velocity of the falling object. So how do we predict how big a friction force will be? One common way to do this is through what's called Coulomb's law of friction. This law suggests that there are only two primary factors that determine how much frictional force exists between a set of surfaces. Normal force, which describes how interlocked the two surfaces are as they're pressed together, and the texture of both surfaces, how rough they are or how smooth they are. This is modeled through a special coefficient. This is the Greek letter m, or mu. Kind of looks like an M and a U put together with a little bit of a tail on one side of the U, making it look like an N. This coefficient of friction can be thought of as a quantitative measure of the roughness of the two surfaces. So the more rough the surfaces are, the bigger this coefficient will be. One property of coefficients mathematically is that they don't have any units. It's just a number. So for most surfaces, mu will typically vary between 0 and 1. 1 would be very rough surfaces, and 0 would be a theoretically perfectly smooth surface. So if we put both of these variables together, we can write a fairly simple formula to describe or predict how big friction will be in a certain case. The friction force is simply the product of the roughness number and the normal force between the two surfaces. Now this applies to both types of friction. In the case of kinetic friction, there is a special kinetic coefficient of roughness number between the two surfaces. In the case of static friction, there's a different roughness number between the two surfaces. Now, static friction also has the special distinction of being able to vary itself relative to the applied force that's acting on it. So this value for my value for kinetic friction is relative constant. When I use this equation, static friction will only grow up to this amount. So we say that this expression is useful for finding the maximum force of static friction. And again, because surfaces typically behave stickier or rougher when the objects are at rest relative to each other, the roughness number for static friction tends to be larger than that for kinetic friction. So how do we know what these numbers actually are? Here's an example of a table of values of static and kinetic coefficients of friction. In page 104 of our textbook, for when you're doing homework problems, you can look up these values as well. So we can see that it always involves a set of two surfaces, so steel on steel or copper on steel. We have to take into account both textures. Now these numbers are general values, and of course rubber on concrete can vary depending on the type of rubber that you have and the texture of that exact rubber. But we see in general that the rougher surfaces up here with the bigger coefficients, then as we move towards smoother sets of surfaces like the joints inside human knee, we end up getting very small numbers, and the numbers approach zero. In most cases, the static coefficient is bigger than the kinetic coefficient, but in some cases they begin to approach each other, like in the case of these very smooth objects. Here's a situation you should be familiar with. Imagine that there's a box on a surface, and an applied force is added to it. We know that there will be a frictional resisting force that will act in the opposite direction. Now, the way that this friction resistance force behaves will be proportional or dependent upon how this applied force behaves. So let's consider a graph in which the applied force is my independent variable, and we examine how friction responds to an increasing applied force. Of course, when zero applied force is offered, the frictional force will also be zero. For 1 Newton of applied force, 1 Newton of friction force must exist to keep the object at rest. And it will continue in this nice linear relationship up until a certain point. At some point, friction won't be able to take it anymore, and we'll reach our maximum force of static friction. The object will begin to slip. Typically at this point, the size of friction decreases and becomes a constant. This constant value is my force of kinetic friction. So if we exert a force on an object, we could typically create a graph like this and determine or find the various friction values from this kind of graph.